What makes this puzzle great, aside from the surprising pi of course, is how well poised it is to be a general problem-solving lesson. Very often when I present this as a lecture, I like to start by inviting the audience to begin by listing out a few general problem-solving principles. You might enjoy thinking of a few of your own, and as we go through, I'll highlight a couple that I have written down here. For example, one that's seemingly trivial but surprisingly useful is that if you're stuck on a hard problem, and I would consider this a hard problem, it never hurts to just list any equations or theorems that might somehow be relevant. So for this puzzle, where we have some colliding blocks, two relevant laws that might come to mind, especially if you have a recent physics class somewhere in your history, would be the conservation of energy and the conservation of momentum. The energy of one of these moving blocks would be 1/2 times its mass times its velocity squared. So let's say we call the mass of the big block m1 and call its velocity v1. And likewise, the mass of that little block will be m2 and its ever-changing velocity will be v2. Then the total kinetic energy between these two blocks is what you get by plugging in the numbers and adding these two quantities. The conservation of energy essentially says this number won't change throughout the experiment. Those two velocities will change, but they have to do so in such a way that this whole expression equals the same number. This is all, of course, assuming that no energy is lost to friction or to the collisions. The other quantity that's conserved is momentum. And the momentum for each block looks even simpler. It's just its mass times its velocity. So again, when you plug in the numbers and you compute this expression, you'll get something. And what the conservation of momentum tells us is that whatever that number is, it doesn't change even after the blocks collide with each other.